Welcome to the third grade. This week we're going to focus on two of the five different standard groups. We're going to focus on operations in algebraic thinking and then number and operations in base 10. So let's begin with operations in algebraic thinking. There are many different clusters within this group here, so be patient as we go through a few examples of each type. And feel free to email me if you've got any questions. Things in the grade levels are now starting to develop more quickly, and they're starting to be more complex for students. All right, so we know that there are multiple different ways in which we can show single-digit multiplication. So in the middle here, I have 5 times 3, which we know from rote memorization that that's 15. So the first way we're going to show is by arrays. So I've created 5 rows of 3. So we can multiply or add 5 plus 5 plus 5 plus 5, or 3 plus 3 plus 3 plus 3 plus 3, etc. Or we can actually individually count them. The second one is repeated addition, which shows from second grade more into the arrays, or in addition to. So I can add 3 plus 3 plus 3 plus 3 plus 3, or we could add 5 plus 5 plus 5. We could create equal groups. We think of this as 5 groups of 3 in each group. So I've got 5 groups of 3 smiley faces, so we could then count that there are 3, 6, 9, 12, 15 smiley faces. Similarly, you could also do 3 groups of 5 smiley faces. Or we could use a number line. You see on my number line that I've got 5 jumps of 3, or we could do 3 jumps of 5. Take a moment, pause the video, and create an array, repeated addition, equal groups, and a number line to represent 7 times 2, which equals 14. So pause the video, come back, and then we'll go through them. So I've got an array. I've got 7 rows of 2, or you could do 2 rows of 7. We could do repeated addition. 2 plus 2 plus 2 plus 2 plus 2 plus 2, or 7 plus 7. We could do equal groups, so we think 7 groups of 2 in each group. So 2 smiley faces in 7 groups, or we could do 2 groups of 7 smiley faces. Further the number line, we can do 7 jumps of 2 or 2 jumps of 7. Using the digits 1 through 9, at most 1 time each, so you can only use the numbers 1 through 9 once. Try to fill in the blanks to make the following problem true. Sarah planted blank blank carrots in her garden. She planted them in blank rows, and each row had blank carrots. Take a moment, pause the video, see if you can't come up with something that might work. Here is one possible solution. There are many because we have the options of using the numbers 1 through 9. Sarah could have planted 24 carrots in her garden. She would plant them in 3 rows, and each row had 8 carrots. Or we could still do the 24 carrots in her garden, but we could do 8 rows of 3. Lots of options. You could do 18 carrots in her garden, 9 rows of 2 carrots, or 2 rows of 9 carrots. Many possibilities. Suppose there are 4 tanks and 3 fish in each tank. The total number of fish in this situation can be expressed by 4 times 3, which equals 12. Describe what is meant in the situation 12 divided by 3 is 4, and describe what is meant in the situation 12 divided by 4 is 3. So the first one, there are 12 fish altogether, we know this. If we put 3 fish in each tank, there will be 4 tanks, just like the picture shows below. Note, this is a measurement model of division. The number of objects in each group is known, and we are determining the number of groups. Describe what is meant in the situation 12 divided by 4 is 3. There are 12 fish. If we want to partition or share them equally among 4 tanks, there would be 3 fish in each tank. This is a sharing model of division. The number of groups is known, and we are trying to determine the number of items in each group. Allie has 18 markers. Her teacher gives her 3 boxes and asks her to put an equal number of markers in each box. Caliber has 18 markers. Her teacher wants her to put 3 markers in each box until she is out of markers. What is happening in these two situations? How are they similar and how are they different? So, both problems are about students putting 18 markers in a box. Allie has 18 markers and Caliber has 18 markers. So, taking a look at each statement and comparing each particular piece of the situation, it says for Allie that there are 3 boxes and Allie will put an equal number of marker in each box. Versus Caliber is putting exactly 3 markers in each box. We need to know how many markers are in each group of boxes, and Caliber, how many boxes of markers will we need? Allie's statement, how many in each group? How many groups for Caliber? Let's figure out how many markers Allie should put in each box. Figure out how many boxes Caliber should fill with markers. Let's model with Allie. Here we see we need to put an equal number of markers in each box. So I'm going to take 18 and keep sharing them until I get an equal number of markers in each box. I see that I would need 3 boxes, and each box would have 6 markers in them. Versus Caliber, we want to put 3 markers in each box. So I will partition out or share 3 markers at a time, count them out, until I get an equal number of boxes. So with 3 markers, she would need 6 boxes to fill. Allie is partitioning into groups. Caliber is forming groups. Or we could count. So assume 3 markers in each box. We could count 3, 6, 9. Well, that's not quite 18 yet. So then we'll try 5. 5, 10, 15 markers in each box. Not quite 18. What if we tried 6 markers in each box? 6, 12, 18. There we go. There are 6 markers in each box. Let's count with Caliber. We know that we're going to put 3 markers in each box. So we'll count 3, 6, 9, 12, 15, 18. We counted 3s 6 times. So there are 6 boxes of markers. Another option is known as the inverse operation. 18 divided by 3 is how many? We know that multiplication is the inverse of division, and we know that 3 times 6 is 18, so the what must be 6. We could use multiplication facts and properties of operations as well. So 3 times 5 is 15, and 3 times 1 is 3, so 5 plus 3 is 18. Therefore, 3 times 6 is 18, and there are 6 markers in each box. A little more explaining with this problem. What they did here was take 6 and decompose it into 5 and 1. So 3 times 5 is 15, and 3 times 1 is 3. Then adding their respected totals, 5 plus 3 is 18. That's a play on multiplication facts and properties of operations. So decomposing numbers into something that students may know more easily is acceptable. Even though 3 times 6 would be just as simple to multiply by as 3 times 5 and 3 times 1, but just a different way a student might come up with a more creative way. Another one would be repeated subtraction. So starting at 18, subtract 3 to 15. 15 minus 3 is 12. 12 minus 3 is 9. 9 minus 3 is 6. 6 minus 3 is 3. And 3 minus 3 is 0. Because we subtracted 3 6 times, there are 6 boxes. And we could keep track of that by the thought process of doing all that in our head and keep track of that by counting on our fingers how many times we're subtracting by 3. Many problems can be solved in different ways. Decide if the following word problems can be solved using multiplication. Explain your thinking, then solve each problem. So Liam is cooking potatoes. The recipe says you need 5 minutes for every pound of potatoes that you are cooking. How many minutes will it take for Liam to cook 12 pounds of potatoes? Pause the video and see if you can't work through this on your own or come up with some explanation on your own, and then I'll talk through with what I would say. I would say that this could be used by multiplication. We could use this as repeated addition. So 5 plus 5 plus 5 plus 5, 12 times 5 minutes for each pound. So therefore, repeated addition we know is the same as multiplication. So 12 times 5. We could use base 10 pieces to figure this out. 12 times 5 is 12 groups of 5, which looks what I've got there. Based on properties of multiplication, 12 groups of 5 gives the same result as 6 groups of 10. So notice that we took 12, halved it into 6, and then I took 5 and doubled it to 10. And 6 times 10 is much easier to think about than 12 times 5, which may be a rote memorization. So notice that it's the same exact length and we have the same exact pieces, but it's partitioned a little differently. But in either case, the final result would give us 60 minutes for 12 pounds of potatoes. Another problem. Mel is designing cards. She has 4 different colors of paper and 7 different pictures she can glue on the paper. How many different card designs can she make using 1 color of paper and 1 picture? Pause the video if you'd like. Otherwise, we'll go on to the solution here. This one can be solved by multiplication. For each of the 4 colors, there are 7 different picture options from which to choose. So 7 pictures on the first color plus 7 pictures on the second color, etc. This gives us 4 groups of 7, so 4 times 7. Using an array, we can help see a visual representation of the 28 possible choices. Note that the pictures could be different. Note that the colors could be different, but this gives one example of what it might look like. So we could add 4 7 times or add 7 4 times. We could individually count them as well. Nina can practice a song 6 times in an hour. If she wants to practice the song 30 times before the recital, how many hours does she need to practice? This would be a division problem since the number of hours needed can be determined by counting the number of groups needed to make 30. 30 divided by 6 is how many? However, we can rewrite this into multiplication by asking how many times 6 gives us 30? Well, we know that 5 times 6 is 30. So she has to play 5 hours if she wants to practice the song 30 times. Owen is building a rectangular tile patio that has 4 tiles wide and 6 tiles long. How many tiles does he need? Let's draw a picture to get an idea of what this might look like. We see that it is 4 tiles wide and 6 tiles long, just as the word problem described for us. We can certainly count the number of tiles, but we can also see that this makes